Hello, this is going to be the first part in my final project for Physics 101. I'm going to be talking about gravitational potential energy, which is topic 5.3 in our book. Okay, so to start, I would like to point out the formula for potential energy. So I would like to also to point out that these two are the same. They're just different notation. I would like to point out that just different books is different notations. So it's always good to know both in order to be able to read different content. So here, I think it's always important to understand what the letters stand for. I think a lot of people get intimidated when we see a lot of letters and just long equations. Luckily for us, this one's fairly simple. So let's say what they are. M stands for mass, and the units that we're going to be using, it's going to be kilograms. That's a standard for physics. Then G stands for gravity, right? And of course, we're going to be using the 9.81 meters per second squared constant, because we're going to be dealing just situations where we're on Earth, so the gravity is always on Earth. And then we have height, or in our book we have that the formula is instead E equals mgy. So it's just, again, different notation. Y stands for the height of the object, but it's the same thing, wide, or h that we're going to be using in meters. Okay. So what we're trying to calculate when we're calculating potential energy is the stored energy from a system that is not currently moving, right? So for instance, let's say that we have a diver on top. Here's our guy, and then that he's gonna dive to the pool. So we would say that he only has potential energy when he's on top of the platform right there, because he's not in movement. He's preparing to jump. So we can actually calculate its potential energy when we look at this image, and we can just straight up use the formula that we have. So E equals mgh in our case. So let's say, for instance, we have a height of 55 meters, so it's not a long jump, and then we have our guy is gonna weigh 70 kilograms. Okay, so we just go straight up and calculate that, plug that into our formula, fairly easy. 70 times 9.81, that's a constant, and then h, which is 5 meters. So we will go ahead and calculate this. I'm not going to do it because this is just the explanation. So I would like to point out that the units that we're going to use when dealing with energy, it's a standard. We're going to be using joules. So our result, it's going to be something, and the units is going to be joules, right? So that's the potential energy that our little guy has right here when he's at the top. But the interesting thing, and this is where the conservation of energy equation that we have right here, it's gonna start coming in play. What's gonna happen when our guy jumps in and starts falling? Then if we use our formula, let's call this initial, and this called final. So our we can calculate it, the initial potential energy, and then our kinetic energy is going to be increasing as this little guy goes down, and our potential energy is going to be decreasing, right? So as we go down in the system, our little guy approaches the swimming pool. The potential energy is going to start going down, but the kinetic energy, it's going to start going up, because we know that the kinetic energy equals to 1/2 mv squared. And as we're falling, we are acquiring some velocity, and the mass is the same. So as we acquire velocity, our kinetic energy goes up in this system. And as we don't have any outside work, there's no external forces acting in our system, we can just cross it out for this example, and just understand that as we when this little guy is about to touch the pool just an instant before, when he's basically on the ground or he's touching the water, his potential energy, it's going to be 0. Here PE equals 0. And why is that? That is because if we use our formula, our height at the bottom is just going to be 0. So we don't have potential energy at the bottom. Okay, so here is using a more fun example. Who doesn't love roller coasters? I really love them. Actually, this is why I chose this topic, because roller coasters are all based in conservation of energy, and in a very basic level, they use the concept of kinetic and potential energy, which I think it's really interesting. So as we can see, potential energy here at the top, it's 100 because we're not moving. I know that some of you guys may know that instant when you're on top of a roller coaster and you're not moving right before just the ride starts. And as we start going down, now we have that potential energy of 50 and we have that kinetic energy of 50. So we start moving, and with movement it comes kinetic energy, and we decrease our potential energy because our height is decreasing, right? Our mass and our gravity just remain constant. So we're losing potential energy because we're losing height, okay? And then here we're at the bottom, so we don't have height at all, but I'm sure we're moving really fast because our kinetic energy is 100. So I would say the peak of speed, it's going to be right here, or velocity, because we're just moving really fast and we have a lot of kinetic energy. As we start going up again and we start gaining some height, we're going to have potential energy again and some kinetic energy, because I don't think we're going to stop. This is like the best part of the ride, when you're going up and then just suddenly down, right? And you have those sensations because like the energy and the velocity is really fast. But roller coasters, other than the work that it's done to lift the roller coaster at the beginning, it doesn't really have any more external work. If you see, generally there are no engines working this part or anything. It's just it's using the conservation of energy concept to be able to go up and down, up and down. And we're just gonna look at a more interactive example right here. So let's go play, and we're gonna see how our potential energy, which is the red in the graph, it's just gonna be increasing. And so let's go to step one. Step one, as our height is increasing, we're getting potential energy. Then for instance, our velocity is really small. We probably have just a fraction of kinetic energy because we're in a little bit of movement. But most of our energy comes from potential energy. And then as we start dropping, again, kinetic energy, it's most of it. We barely have some potential energy. And then velocity, it's 20 meters per second, which is quite fast. I'm sure that's why we all freak out when we're on a roller coaster. And then as we reach 3, we're again gaining some height, but we also have mostly kinetic energy because we're still moving really fast. On step number 4, we have slow velocity because we're on top of the loop right there, but we're also moving. We really don't stop moving, so we're gonna have some kinetic energy as well. But since we have some height, we're gonna have mostly potential energy there. Then step 5, again, we don't have height at all, so all of our energy is coming from kinetic energy. Then on step 6, we have a little bit of height, but also a little bit of of speed or velocity, so we have just a little bit of both. So that's just gonna it's just a more graphical way to understand it. Okay, now let's jump into our problem right here, which is we have a 20 kilogram a 0.20 kilogram stone is held 1.3 meters above the top edge of a water well and then drop into it. So let's draw a diagram right here, right? So this is 1.3 meters. So I guess this is a well, so we can put a well right here. And then we're given that our height is 1.3. I always like to understand what our givens are. And then a depth of 5 meters. So the depth of the well, it's gonna be 5 meters. And then so this is, let's just call this, the well is right here. The well is just right here. And this is our rock. And then the stone is held 1.3 meters above the top edge of a water well. So we are asked, before the stone is released, and B, when it reaches the bottom of the well, what is the change in gravitational potential energy of the system from release to reaching bottom? Okay, so we're going to release our rock, and it's going to start falling, and then we're going to have some energy come in from that, changes in energy that come from that. So our first height, we don't want to be tricked here. Our rock has a total height of 5 meters plus 1.3, 5 plus 1.3, which is equal to 6.3 meters, our initial height. So we're just going to call H initial, right? And then our mass, it's going to be 0.20 kilograms, right? And then our gravity is just a constant, so 9.81 meters per second, which is just our constant. Again, if we're dealing with moon gravity, it might be different, but we're just gonna stick to 9.81 meters per second here. So we're asked, before the stone is released, what is the potential energy? So when the stone is, before it's released, we just plug all these numbers into our formula right there, which is basically just multiplying them all together, 0.20 and 9.81 meters per second. And then if we plug that into our calculator, 6.3 times 0.20 times 9.81, we're going to see that the potential energy initial, it's going to be 12.3606 joules. So when the rock is not moving, right here at the top, it has a stored energy of 12.3606 joules. And of course, since the rock is not moving, the kinetic energy of the rock is just going to be 0. Okay, so that's for part 1. Let's just keep it there. Okay, now we are asked to calculate, we have part A, before the stone is released, and then when it reaches the bottom of the well, what is the potential energy going to be like? So when the rock just travels all this distance and just reaches the bottom, it's going to have a 0 height, so it's going to be at 0 meters. And then the mass and the gravity, they're not really going to change. So we can just straight go ahead and plug that into our formula right here. So let's do 6.3. And then, I'm sorry, not 6.3, that was for before. We don't want to confuse ourselves here. So potential energy, or height or let's start with the mass. The mass is going to be 0.20 kilograms times 9.81, which is our gravity, times our height, which is 0 in this case. And we know that if we multiply by 0, the whole thing is going to be 0. So we can see that PE final, it's going to be 0 joules. For instance, we can calculate what our kinetic energy would be using the formula 1/2 times mv squared. But we know that energy it's conserved. It's the principle of conservation of energy. So we don't have to do much work because using our formula from the beginning, we know that kinetic energy plus potential energy initial it's going to be equal to final plus final in the case that we don't have any additional work that goes into our system. And in this case, again, we don't have any additional work, so we can see that our kinetic energy is 36.06 joules. And we don't have any potential energy anymore because we're at the bottom. So this is just an example. What is the change of potential energy from the system? So we know that let's just do the change. We're going to do it right here at the end. So we usually use delta in physics to refer to the change. Delta PE is just going to be equal to PE initial minus PE, my bad. P is going to be PE final minus PE initial. Alright, so our final is 0 and our initial is 12.3606. So our delta PE is just going to be equal to minus 12.3606, which of course makes sense. We don't want to forget about the units, so joules. So as the rock started going down, we just lost potential energy, and all the energy was transferred to kinetic energy, which is the energy that we have when there is some type of movement. So now we know how to calculate the potential energy. So why don't we discuss some things that we can do, examples and applications. So anything that it's raised, it's gonna have some type of potential energy. Anything that has some height, some mass, and it's just on a system that has some gravity is gonna have potential energy. And some of the uses that this can have is water that is behind a dam. So of course, we know that we're trying when a dam is trying to create energy, so it's using the potential energy of the water at the top of the dam in order to produce some energy that we're gonna extract and then use. Part that is at the top of the hill, so that's just the same example as the roller coaster. Snowpack. So if you like skiing, then you understand how the avalanches just start, just because the snow that it's there at the top it just has a lot of potential energy, because I'm pretty sure it had some weight. A yo-yo, before it is released, again, it has some weight, it has some height, and it has it's on a system that has gravity. River water at the top of a waterfall, again, just the water is falling, it has some height. Book on the table before it falls, and a child at the top of a slide, and a ripe fruit before it falls. So I believe that some of the important applications that potential energy can have, it's clearly on just on the field of energy. So when let's say we're talking about sustainable energy. For instance, let's just focus on water that is behind a dam. Everything's based on the principle of potential energy, right? So we're using the potential energy that the water has in order to create some more energy. And of course, there's some mechanical energy and some other more advanced concept into it, and then we convert it into electrical energy. But we're basically, what we're trying to do when we're using a dam and we're using the water here, and then the water is just going down here and then coming out again here, we are basically extracting the potential energy of the water, and we're storing it, right? So I just believe, if you look at countries like Denmark, for example, that are basically 100% sustainable energy, they they have one of these in almost every single one of their waterfalls, just because, or yeah, on their waterfalls, because they know how to use the potential energy, in order to create and store energy, in order to avoid the use of and oil and natural gas, or chemical energy. So I think that the highlight here is that we need to understand that we can take advantage of the potential energy, that exists thanks to the gravity, that the Earth provides, and we have developed advanced methods in order to extract some of the potential energy that, for instance, a water dam can have, in order to create sustainable energy that doesn't damage our environment.